Section 3.5 deals with implicit differentiation. Now, currently, we can differentiate any function that is explicitly solved for a variable, which means it can be expressed as a function in one variable, kind of like y equals 2x squared plus 16 or f of x equals 2x squared plus 16. I can solve that for y. But if I look at something like 2x squared plus y squared equals 16, I can't solve that explicitly for y. I can solve it for y squared, but I can't solve it explicitly for y. So in order to find the derivative of something like that 2x squared plus y squared equals 16, what I can do is I can do implicit differentiation, and that allows us to take derivatives of equations that can't be expressed as functions of one variable. So before we look at implicit differentiation, just a couple of things so that you know the notation of what we're looking at. First off, d dx is the derivative of x. dx over dx is the derivative of x with respect to x. And dy dx is going to be the derivative of y with respect to x. And that's the same thing as y prime. So how do you do implicit differentiation? Well, all the rules that we know for derivatives are still going to apply. So the power rule, the chain rule, the product rule, the quotient rule, none of those change. So we're going to still take the derivative just as we normally did. We're going to differentiate both sides of the equation with respect to x. So make sure that for any term involving a y, we write dy dx or y prime. So if I take the derivative of 2x squared, again, I'm going to use the power rule. I multiply this to the front, so that's 4x, and it's raised to 1 power less. So 2 minus 1 is 1, so it's 4x to the first, or just 4x. And I'm also going to write this. I just took a derivative of an x term with respect to x, because that's an x term. Then plus, let's take the derivative of y squared. Well, again, I'm just going to use that power rule, bring the 2 out in front, y to 1 power less, so it's going to be y to the first power. And then times, I just took the derivative of a y term with respect to x. Equals, well, the derivative of a constant is 0, so I just write 0. Now, we aren't going to write dx anymore. I just wanted to kind of show you what's going on here. So basically what happens is when we take derivatives of terms with respect to x, if we were to write dx over dx, well, if you have the same thing in numerator and denominator, it's going to cancel. So we never wrote that, but we were taking the derivative of an x term with respect to x all along in all the sections before. So now what's happening is if we end up taking the derivative of something that's not an x term, we need to put in our dy dx here. So I'm just going to clean this up and rewrite this as 4x plus 2y. And instead of writing dy dx, I'm going to have y prime here. And the book uses y prime, so we want to kind of get used to the y prime. So step 1, differentiate both sides with respect to x. And for anything that you are taking the derivative of that is not an x term, make sure you write your y prime. Step 2, solve the resulting equation for y prime in terms of both x and y. So I need to solve for y prime, which means I need to get y prime all alone on one side of the equal sign. So I'm going to start by subtracting off my 4x. So then 2y, y prime is equal to negative 4x. And again, I need to get y prime all alone. So I'm going to divide both sides by 2y. And I end up with y prime is equal to, well, negative 4 over 2 is just negative 2. And then I can't reduce between x and y, so it's negative 2x over y. So the derivative of 2x squared plus y squared equals 16 is negative 2x over y. All right, let's go ahead and do another one of these problems. So use implicit differentiation to find y prime, and then evaluate y prime at the indicated point. Okay, so let's just look at the first part. Use implicit differentiation to find y prime. So let's take the derivative, and again, anytime we take the derivative of a y term, we're going to write y prime. So let's start with our first term, x cubed. Well, the derivative of x cubed is 3x squared. Plus y cubed, the derivative of y cubed is 3y squared. And since we took the derivative of a y term, we're going to write times y prime. Plus the derivative of y. Well, the derivative of y is just equal to 1. Remember, the derivative of x is just equal to 1, so the derivative of y is just equal to 1. And again, we just took the derivative of a y term, so we write y prime. Minus the derivative of 2 is 0 because it's a constant, equals the derivative of 0 is 0. Okay, so now we need to solve for y prime. So everything that's a y prime needs to stay on one side of the equal sign, and everything that isn't needs to go to the other side. So I need to subtract my 3x squared from both sides. So I end up with 3y squared y prime plus 1y prime is equal to negative 3x squared. I need to solve for y prime. Well, we might notice that over here, we have y prime in each one of those terms. So I can factor out a y prime, and if I factor out a y prime from each one of those terms, I'm left with 3y squared plus 1. So now, divide both sides by your 3y squared plus 1, and you end up with y prime is equal to negative 3x squared over 3y squared plus 1. So the derivative of x cubed plus y minus 2 equals 0 is negative 3x squared over 3y squared plus 1. And nothing can be canceled with this. Don't try to cancel these 3's because they cannot cancel. In order for it to cancel, it would have to come from all 3 terms, so nothing will cancel in this derivative. So that, again, is implicit differentiation, but the next portion here asks us to also evaluate y prime at the indicated point. Well, the indicated point is negative 2, 2. So it tells me that my x value is negative 2 and my y value is positive 2. So all this is asking me to do is find y prime at the point negative 2, 2. So anywhere I see an x, instead of writing my x, I should write negative 2. And everywhere I see a y, instead of writing my y, I should write a positive 2. And then all I need to do is just work this problem out. Well, this is going to be negative 3 times 4, which is negative 12 all over. Well, 3 times 4 is 12 plus 1 is 13. So y prime evaluated at the point negative 2, comma 2 is this negative 12 13ths. Okay, let's look at the next problem. Example 3. Again, we want to
use implicit differentiation to find y prime,
and then evaluate y prime at the indicated point. So find y prime and evaluate y prime at the point. Directions are the same for this until the end. How do we do this? Well, first let's start by finding y prime. Let's start by finding the derivative. Now be really careful here. Notice that in the middle here, this is negative 2xy. When you have variables right next to each other in math, that means that they're multiplying, which means what I've highlighted in blue there is a product. So I'm going to have to treat that as a product rule. So I'm going to go ahead and label my first and second for that product rule now, and then take the derivative. So if I label, well, I'm going to say that my first term here is negative 2x, and that my second term is equal to y. This is my second, and this is my first. So then the derivative of my first, f prime, the derivative of negative 2x is negative 2. And the derivative of y is 1 times y prime, because we just took the derivative of a y term. So now let's find the derivative. So the derivative of x squared is going to be 2x. Then I need to do the product rule. So I'm going to say plus, and ignore that minus because I assigned the minus sign to the first term. So I'm going to write plus, because remember, we can always make anything into plus a negative, and I would definitely recommend you doing that so that you don't forget to distribute negatives in the end. So plus, and then remember it's going to be the first times the derivative of the second. Well, the derivative of the second was that 1 y prime. The first times the derivative of the second plus the second, which is y, times the derivative of the first, which is negative 2. And then that equals, well, the derivative of our last term over here, the derivative of 5 is 0. So the derivative of x squared was 2x. That negative 2xy was a product. So I made it plus a negative. I assigned a negative 2x to my first term and y to my second term. I used my product rule in the middle there. And at the very end, I said that the derivative of 5 was equal to 0. Now let's just clean this up and solve for y prime. So let's see here. We have 2x. If I multiply a negative 2x times a 1y prime, I get a negative 2x y prime. And if I multiply a y times a negative 2, I get a negative 2y equals 0. So again, everything that's not a y prime needs to move to one side of the equal sign. So I'm going to say negative 2xy prime is equal to, moving both of these over, I'd get positive 2y minus 2x. Then I need to divide everything by a negative 2x to solve for y prime. And then move it right here. So then y prime is going to equal 2y minus 2x all over negative 2x. And now notice that every single one of these numbers is divisible by 2. So I can reduce out of 2 if I want to. So y prime will be equal to y minus x over negative x. Great, so here's my derivative. So find y prime and then evaluate y prime at the given value. Well, I'm given what x is, but I don't know what y is, right? So how do I find y? Well, I'm going to have to plug x into this original function and solve for y so that I can find my y and then evaluate y prime at the indicated point because I need a y. So what I need to do is plug in a 1 in place of the x's and solve for y. So I get 1 squared minus 2 times 1 times y is equal to 5. So I end up with 1 minus 2y is equal to 5. Subtract 1 from both sides, and I get negative 2y is equal to 4. Divide both sides by negative 2, and y is equal to negative 2. So now I know what x is and what y is, so I just have to evaluate my y prime at that indicated point. So y prime evaluated at 1, negative 2 is going to equal, well, negative 2 minus 1 over negative 1. So negative 2 minus 1 is a negative 3 over negative 1 is a positive 3. So at the point 1 comma negative 2, we get a value of 3.